All right, welcome to week 7, our second to last week of summer chem prep. Today we're going to be talking about chemical reactions. We'll probably start with some of the stuff that you've already heard of, already done before, and then it might get a little tricky at the end. Okay, but just in general, whenever we're writing chemical reactions, we always have the same setup, right? We always put what we're going to call our reactants on the left, and then we put a little arrow that just means all of these reactants are reacting together to produce whatever our products are. Okay, so that's the general setup. Now what this in reality could end up looking like is that you have multiple reactants, multiple products, right? So you could have reactant 1 plus reactant 2, so on and so forth, going to produce product 1 plus product 2, product 3, for however many reactants and products you have, okay? So you've probably done that before. You've probably written chemical reactions. Now, what we have to make sure of, and where it gets kind of tricky, is we have to make sure that all of these reactions that we're writing adhere to a very important law in science, and that is the law of conservation of mass, or conservation of matter, it's sometimes said. And you probably have already heard of this. So what that says is that mass or matter cannot be created or destroyed, right? Whatever mass or matter we have in this universe, we've always had, it will always be here. We cannot create more or destroy any of it. How that plays out in chemical reactions is just, and it's, much more microscopic scale, but what we're saying is any atom that goes in as a reactant must come out as a product, right? So let's say in all of your reactants you have a total of, 12 oxygen atoms, right, among all the other atoms, but 12 oxygen atoms go in through your reactants. All that says, through the law of conservation of matter, is that 12 oxygen atoms then must come out, okay? So in order to adhere to that law, we're going to do what's called balancing chemical equations, and so that's what we're going to do next. Okay, so balancing chemical reactions. Now, I'm going to do kind of the same setup that I did for the Lewis structures last week, where I'm going to do an example over here on the left while I write out the steps to balancing chemical reactions on the right. Okay, so here is our example reaction. We have calcium chloride reacts with aluminum to produce aluminum chloride and calcium, right? So just by reading this sentence, you should be able to distinguish what is a reactant versus what is a product, right? And it's this phrase right here, to produce, that kind of separates the reactants and products, right? We have calcium chloride reacting with aluminum. Those are our reactants. And then those two things react to produce aluminum chloride and calcium. So those are our products. So the first step in balancing chemical reactions will be write formulas for all reactant products. Okay, so let's do that. Calcium chloride, you guys should be able to write the formula for that. Calcium is +2, chloride, or just chlorine, is -1, and so we would need CaCl2. Reacts with aluminum, that's just regular old aluminum, so that's just Al. To produce, so we put our little arrow, and then aluminum chloride, aluminum, if you look on your periodic table, is +3. Chlorine, again, is -1, so we would need AlCl3 plus calcium, Ca. Okay, so that's the first step. A lot of times this step is already done for you, but just in case it's not, you will have to do that first. And then number 2, you want to count number of all atoms present on both sides. Okay, and both sides here we're just meaning on the reactant side and the product side. Okay, so this is a pretty simple equation to have to do this for. So let me just show you what to do. Basically, until you get really good at it, what I like to do is kind of make just a list down the middle of all of the elements that are present, right? We have calcium, we have chlorine, and we have aluminum. And then basically, I'm just going to make a list on the left, how many of those atoms are present on the left, how many of them are present on the right. So calcium, we have 1, chlorine, we have 2, aluminum, we have 1, all on the left, the reactant side. On the right-hand side, we have 1 calcium, 3 chlorine, and 1 aluminum. So the law of conservation of mass just tells us that when we look at these numbers, they have to be the same on the left and the right. If they are not, then they are in violation of that law, and we have to fix it. And so you can see we are in violation right now, and so we're going to have to do another step. But before we do that, I just want to go through this counting process for a little more tricky compounds, because these are relatively simple. So just as a quick aside, I just wanted to do a couple formula just to show you what could be presented to you maybe when we do some group work. All right, so these are all formula of just different compounds, right? But they're a little more intricate than the ones we're using in this example. So I just wanted to give you a kind of trickier example of counting up atoms in a compound. Now this first one, you could probably see there's 1 calcium, 1 carbon, and 3 oxygens, right? That's not that tricky. But here we get into compounds that must be written with little parentheses, okay? These are called polyatomic groups because they're groups that have multiple atoms, so polyatomic. But how they're written, you have these polyatomic groups in parentheses with little subscripts outside of those parentheses. And what that means, if you kind of think of it like math, this is just going to distribute this subscript that's right outside the parentheses, distributes to everything inside the parentheses. And basically you're just going to multiply, just like if you were distributing a coefficient in math into something in parentheses, you multiply the numbers together to figure out the total, right? So this calcium, since it is not in the parentheses, there's just 1. But then when we get to nitrogen, you see how there's 1 nitrogen inside the parentheses, but then there's 2 here. So we have to multiply 2 times 1 to get 2 total nitrogen atoms. Likewise, for oxygen, there's 3 inside, but there's 2 of them. So 2 times 3 means 6 total oxygens, okay? For this one down here, there's 1 nitrogen in here multiplied by 2, so 2 total. 4 hydrogens multiplied by 2, so 8 total. And then the S and the O's are outside the parentheses, so you don't distribute that number, obviously, to them. That would just be 1 sulfur and 4 oxygens. So be careful if you see compounds that have parentheses in them with these little subscripts outside. You do have to distribute those subscripts across. Okay, so back to our example. I've gone ahead and written step 3, which is the actual balancing part, right? But what we're going to do is use coefficients to balance out the number of all atoms, okay? So let me kind of squeeze this in here a little bit, because we are going to write coefficients out front of all reactants and products in order to balance these number of atoms out in our reaction. So you can see that calcium's already good, aluminum's already good. Those aren't the problem. The problem is the chlorines, right? So we have 2 chlorines on the left, 3 chlorines on the right. How are we going to get those to even out? We're again going to look to the lowest least common multiple, right? That's what it's called, the least common multiple between those two amounts. So 2 and 3, the least common multiple is 6. So how could we get this 2 chlorine on the left up to 6? Well, we would put a coefficient that would multiply all of the numbers in the compound, all of the element amounts in that compound by the coefficient amount. So if you put a 20 here, you would multiply the number of atoms by 20. Or if you put a 7, you would multiply it by 7. But we just need to get that 2 chlorine up to 6 chlorine. So what would you multiply it by? 3. Good. So now we don't have 2 chlorines, we have 6. But we've also changed the number of calciums, right? Because that's in the compound that we put the coefficient in front of, we also have to update that count. So now that's 3. We can come back over to the right side because we, again, are trying to get 6 chlorines. We would only need to put a 2 here because 2 times 3 is 6. But again, that also changes aluminum, right? Because that's included in the compound. So now we have 2 aluminums. So in the process of evening out chlorines, we've actually screwed up calcium and aluminum, but that's okay because we can just add a couple more coefficients to balance out everything else. So let's go back to calcium. We have 3 on the left, 1 on the right. We need 3 total, so 3 times 1 will give us those 3. And then aluminum, we need 2, so we'll put a 2 coefficient there. And now you can see calcium's 3, 3, chlorine is 6 and 6, aluminum is 2 and 2, and we are balanced, okay? Now, we're going to do a couple trickier ones. So let me give you a hint down here that will really come in handy when we do the trickier ones and the group work in a little bit. So the hint is start with an element that only shows up once on both sides of the arrow. Okay? You want to start with an element. You know how we started with chlorine, trying to balance out chlorine because that was the only one that was not balanced. But if you have an option, you want to start with an element that only shows up once on the left side, the reactant side, and once on the right side. So again, this was a simple one. So every single atom only shows up in one place, right? Calcium only shows up in this compound on the left, and it only shows up here on the right. Chlorine only shows up in this compound on the left and only shows up in this compound on the right. So this was an easy one. We'll see this in the next examples that we do. Well, the second one. We're going to do 2 more examples that we're getting a little trickier here. Okay, so keep that hint in mind when we do the next one. All right. So I'm not going to make you write this one for the sake of time. So I'll just give you the formulas. So it's going to be K2S plus GaF3 goes to KF. I'm running out of space here. KF plus Ga2S3. Okay, so it's a little cramped, but hopefully you can see that. So we've got the formulas written. Now we need to count all of the atoms. So let's make a list. We've got potassium, we've got sulfur, we've got gallium, and we've got fluorine. Okay, and so now we just need to count both sides. So potassium, and these are just colons. They're not like electrons. So I can just put little equal signs here so they're not confusing. But Potassium atoms on the left, we've got 2, we've got 1 on the right, sulfur 1 and 3, gallium 1 and 2, fluorine 3 and 1. Okay, so there are our current counts. And so now our next step would just be to apply these coefficients out front in order to balance them, because right now we've got nothing balanced. So we've done our count, now we're going to use coefficients. We're going to, again, you want to start with an element that only shows up in one place on the left and one place on the right. This again is, it doesn't matter because they all show up once on the left and once on the right. So just randomly pick one to start with. So I have potassium written first, so I'll just do potassium. So we have 2 on the left, 1 on the right, so let's put a 2 here. That's going to change that potassium count to 2, but it also changes the fluorine amount to 2. Now, I'm going to go to this one because this could be a little tricky, right? We need to get this to be equal fluorines. We have the 3 and the 2, so again, least common multiple would give us 6. So let's try to do that. We need 2 there, so that'll give us 6 here. It also changes gallium, so don't forget to update every element. And then we're going to have to erase this 2 that we just put, and that's fine. A lot of times that will happen, and we're going to end up putting a 6 there. That changes this fluorine count to 6, but it also changes the potassium count to 6 as well. So we can just go right back and do the potassium. We need to get this potassium on the left up to 6. So let's make that 3. We'll make this 6. And now we have 3 sulfurs as well. And you can see just by doing that, we were working on potassium, but by balancing out potassium, it also balanced out sulfur, and we didn't even have to do anything to that last compound. Okay, so now you can see 6 and 6, 3 and 3, 2 and 2, 6 and 6. Your coefficients are 3, 2, 6. And here we did not put anything. That just means a 1. You'll find that a lot in chemistry. If there's no number written, you just assume 1. So you actually do not have to write a number out front. If there's no number, you just take that to be 1. Okay, last one, and this is by far the hardest, but it's really important because a couple tricky things come up during this one that I wanted to show you. So I've already written the formula, so we're good on step 1. Step 2, let's just count the number of each element. So we only have carbon, hydrogen, and oxygen. So let's go through and figure out how many of each. Carbon, we only have 2 on the left, 1 on the right. 3 hydrogens to 2 on the right. And then oxygens here, notice how we have 2 reactants with it, so we do have to put the total number of oxygens, so we'll have 4. And then the same thing over here where we have 2 products, so count the total number of oxygens, so it'll be 2 plus this 1 gives us 3. Now finally we can use this hint, right? We want to start with the element that only shows up once on both sides of the arrow. So using that hint, you can basically eliminate the element that you should not start with, right? Because there's only one element that does show up in multiple places on the left and the right, and you can see very clearly it's oxygen. Oxygen shows up everywhere. So oxygen is going to be the hardest element to balance, so we save it for last, okay? A lot of times it'll kind of just work itself out if you save that hard one for the last element. For this example, it's going to be a little trickier, so you'll see. But basically, we can start with carbon or hydrogen, again, because they only show up once on both sides. So let's go and start with our coefficients. So you can pick any one. I'll just choose, again, the top one listed. Carbon, we're going to need a 2 there, and that's going to change this carbon to 2. And the oxygens, now we have 4 plus this 1 to make it 5. Okay? Then we can go down to hydrogens. we've got 3 on the left and 2 on the right. Again, we're going to have to play least common multiple game. And so even though we just did the carbons, it's going to end up changing because we need to put a 2 here to get that to 6. What we're also going to change is the carbon and the oxygen, right? So now we have 2 times 2 is 4 plus another 2, which is 6. And then we'll have to come back over and eventually change these. So let's just finish out hydrogen. We were making them 6, so we'll put that as a 3. And then we need this carbon to go up to 4, so we'll put a 4 there. We can kind of kill 2 birds with 1 stone. This goes up to 4. Now the hydrogens go up to 6, and the oxygens are getting a little tricky here. We've got 4 times 2, so that's 8, plus 3 more from water, so that's 11. All right. So here comes the tricky part, because carbon is done, hydrogen is done, oxygen is the only one left. Now look at these numbers though, and you're going to have to kind of play some little math game in your head. But if you notice, see over here are 2 sources of oxygen, both have subscripts of 2. So no matter what coefficient you put in front of either of those reactants, what type of number are you always going to end up with for oxygen? It's always going to be an even number, right? Because anything times 2, anything times 2 is always going to be an even number. But look over here. We've got an odd number of oxygens. Therefore, we're never going to get these to balance out as long as this is an odd number on the right. We don't have to worry about this because it's, again, a 2, so it's going to be even. It's this oxygen that's really throwing us off. So we need to get this to be an even number because that's the only type of number we're going to get on the left. Can you think of anything we could do to very quickly solve this problem? Because again, anything multiplied by 2 would be an even number, right? So let's just multiply all of the numbers that we just put up here by 2, and then we will have universal even numbers, okay? This happens a lot, so keep this in mind. If you ever have a situation where one side is even guaranteed, the other is odd guaranteed, double everything. It makes everything even, okay? So therefore, we now, instead of a 2, a 4, and a 3, we've got a 4, an 8, and a 6, because we're just doubling everything. All this does is double, double, and then the oxygens are going to be a little trickier, right? So we've got 8 plus 2, so that's going to be 10. But here on the right side, now we've got 16 plus another 6 for oxygens. So that's going to be 16 plus 6. We've got 22. It just doubled, okay? But now, all even numbers, we can now finish this off. So we need 22 oxygens. We've already accounted for 8 with this compound. So we just need how many more? 14 from O2. So to get 14, you need 7 O2s, and that would give you 22. Okay, so that's kind of as tricky as it can get, but keep in mind this hint and this little trick of doubling everything if needed. All right, that's it.